Okay, so once again, good morning, gentlemen, and welcome to today's class. We started last week with introduction. We laid a foundation. We discussed about piping, the sizing, and everything. So this morning, we're going to treat a case study. And this is the way I think is proper to learn. You lay the foundation, then you go to case study, then you go to computer application. So what you have on your screen now, wondering how I can make it bigger. I don't know. Should have opened it with PDF. So let me open it with PDF. So this is a case study. Open it on your system. Don't have option. Same Adobe. Okay. So this is a case study. All of us can see it.
It's your drive that we are seeing.
Yes, you are not sharing the case study.
You can see it now?
Not yet. Now, yeah, we can see it now.
Yes, we can see it now.
Okay, sir. So this is a case study. It's just a small case study. So we'll start and finish it. It's easier for us. Now, when you are asked to design a water reticulation system or water distribution system, it's the same thing. The first thing we said last week is that you need a map. So you'll be given a map. But we say we need a map and with topography. That is why the first person that goes to site in the water reticulation design is the surveyor. The surveyor goes and takes the spot height. Why do we need the spot height? Why do you make sure you have the levels? Because 99% of water reticulation systems are via gravity. Because of energy, because of cost. Now, it means that if you need to identify the lowest point, you need to identify the highest point. Why do you do that? Because water will flow from the highest point to the lowest point, and there's no pressure, there's no pumping in the system. So that's why if you come to a community, you take your spot height, you know where are the lowest buildings and where is the highest building. Your elevated tank is going to be located at your highest point. And of course, most likely, your water source is going to be located at the river, the lowest point, groundwater. So it means you will need a pumping from your water source to elevated tank. That is called transmission network, usually one pipe. That is transmission network. And you design it based on daily values. You design your transmission network based on daily values, and you design your reservoir tank based on daily values too. But your pipe network will be designed based on hourly value. And that brings us to distribution network. So there's a transmission network and there's a distribution network. Now, the distribution network is what you're going to design, because the transmission network is very simple. I mean, based on the water requirement, your tank size, and then the rate of extraction, of course, you cannot test more than the recharge rate of the aquifer. And in the treatment, in terms of the surface water, you cannot supply more than the production rates of the water treatment plants. So that one is fixed, it's simple. Based on your population equivalent, you know the daily requirement. We did all that last week. So now, you'll be given a map, the topography. As a consultant, you'll be asked to design the water reticulation systems, and that is what you have before you. So looking at this map, it's obvious to me that we have elevation system from 320 to 250. If you supply 320 from 250, that will give you 70 meters. And 70 meters is like 7 bars. We talked about it last week. 7 meters is like 7 bars. It is in your test. So, and we said that your network must not be more than 80 bars based on German standard anyway, which is also that would apply here. Once the head difference between the water source and the lowest point in the network is more than 8 bars, then you need to provide pressure zones, or you need to provide a cascade, or you need to provide buffer tanks. You need to have a way to cut off the pressure, break the pressure. And of course, you know how we break pressure. You just create a reservoir midway, okay? And then those who are at the lowest end will now take their supply from the middle reservoir, while those at the upstream will take their supply from the upper reservoir. If you are confused, don't worry. All these things are in those tests, chapter 1 to chapter 10. So by the time you're going through those tests, what we are discussing in this class will start to make sense. So if it doesn't make sense, just calm down because we have only 3 weekends for this. Now, your job is to design this network. So what you see here is road. So this is the road. The black dots are houses. So you will see houses on the left and on the right side of the road. This is very a simplistic view, but it could be bigger than this. It could be huge. It could be an estate. It could be a district, just like we designed last week. I asked us the assignment you gave us. In the case of a district, all you need to do is to design what is the maximum water going to Wuse, going to Lekki, going to Ikoyi. By the time they get to Ikoyi, you now start to distribute the secondary pipes. Remember, we talked about primary pipes, which is the big one, coming from the tank, okay, running parallel to the street. And then we now have the secondary tanks, the secondary pipes, taking water from the tributary of the primary pipe. And then we now have the tertiary pipes. And we said that the primary pipes sometimes can be like 1 meter, 1.5 meter, 900. The secondary pipes can come down to 600, 300, 450. Then the tertiary pipes can come down to 75, 100 mm, 150, and so on and so forth. So you can see the cascade. As the water is going downstream, the pipes are going down, are reducing in value. So now, let's go again. So as a designer, by the time you finish your distribution network, you're going to get something like this. Yes, if you look at it, this is synonymous with the road because the pipe will follow the right of way. You don't put pipe along people's plots or under their foundation. So you follow by the side of the road, either on the left side or on the right side. So ideally, you just provide one pipe. We expect you to provide one pipe because what we are doing is just water demand. All those dots you see here are nodes. So each of these nodes controls beginning of the street, end of the street. So while I'm still talking, you can look at the pipe, you can look at the, you see that this thing is just a replica of this. So this becomes your distribution network. And if you go to chapter 8 of the manual I gave you, you could also see the background. Where is chapter 8? Okay, I think it's on our WhatsApp. Should be somewhere here. Okay. So somebody should open chapter 8, please, while this is going on.
Hello? Can't hear anything. Is anyone talking?
I was about to ask the same question.
I think he's from his end, though. His
No, he's
network,
no
maybe.
longer here. You lost him.
Yes, it's from his end. I guess so.
I think he asked before he left if anyone can share chapter 8, but it's like sharing is disabled by the host. So he has to.
I've requested that he enable, but he has not enabled yet.
Okay, maybe his network is down.
We can't share anything.
Yeah.
Okay, sincere apology. So let's continue. My network went off. Okay, so go back to screen sharing. So this is the network. So to further do this, you prepare a sheet that looks like this. This is your design sheet. For every water reticulation design, you need to prepare a sheet like this. Also, it also applies for stormwater. Anything pipe design, you need to prepare something like this in Excel. It's very, very important. It's synonymous with design.
Rotate is in edit. Edit.
Sorry?
Edit.
Date of what?
Rotate. I thought you want to rotate.
Yeah, I'm looking for it. I don't know this kind of, sorry?
Under edit now.
Under edit.
Edit. Rotate.
Okay,
Yeah.
No. Can't believe it.
Close that one.
Just cancel that one.
Rotate again.
Rotate. It's okay. Can't believe it.
Just go to the left-hand side and look at that symbol.
Yeah, okay. You can open the main document where it was prepared, if possible.
It's still the same thing. Left-hand side where you have to operate.
Okay, just
another.
I think you can just right-click on the document. You'll see.
Yeah, I did it. It is not giving me more option. You see, you can see no open with. I'm looking for open with. There's no open with here, and this is crazy, man.
Open with is there.
Yeah, it's not giving me option of open with. Oh, it's here.
Open with is there.
Adobe.
Yeah.
It's using the latest Adobe.
Yes. Okay. Have you tried right-clicking on the table itself? Just put your mouse, your cursor, and right-click. I think you should see options of rotate. Yeah, see rotate on top. The second option.
Giving me to try to buy. It's okay. Let's continue, gentlemen. Rotate your own. I'm familiar with it. So the first.
I think we can even see with what is there. We can read it now.
Yeah. So if you look at now, gentlemen, you see this sheet you have here is one of the most important things you need to prepare. You need a sheet like this. And mind you, like I said, anything pipe design, whether it's gas pipe design, water pipe design, or drainage design, sewer design, you must prepare a pipe. Because pipe talks about nodes. It talks about sections, right? For instance, now, if you look at this place, it says section ST, storage tank 2.1. This one says section 1 to 2. This one says section 1 to 4. So for instance, storage tank to section 1 simply means from here to here. You get it? Then 1 to 2 means from here to here. 1 to 4 means from here to here. So you could see that here we have a node. Here we have a node. To connect two nodes is a pipe. This node also represents where your water meter will be located, more like a manhole. Now, what we're doing is a proper standard design. Not so complicated here. Where you see somebody putting a manhole and just burying it. No, there should be an inspection chamber, a standard. Peradventure, you want to do maintenance along section 1 to 2, along section 4 to 3. You can go to the manhole and lock off the water meter there or off the valve there. So these nodes represent, more like inspection chambers, more like point of intersecting two streets. It also serves as a place where you can put your water meter and measure what is going to a zone, to a district, or to a layout. It also means where you will determine the water design. For instance, look at node 6. Node 6 will service, look at node 13. Node 13 will service all the houses that are between 6 and 13. You look at node 11, it will service all the houses between 7 and 11. So, we cannot start putting nodes to every houses. So what we do is that we sum everything inside one node. Okay? For instance, look at all the houses. This is node 6, and this is node 13. All the houses between 6 and 13 are being serviced by the node at 13. And so on and so forth. Here is node 4. And here is node 3. So all the houses along this corridor, their total value of water requirements, you just put the value as the node demand or water demand or the water flow in node 3. Did you get the point? Okay. Let me further demonstrate this by opening my whiteboard. Let me just share something on the whiteboard. So this is my whiteboard. So let's assume there's a house here. Then there's another house here. Okay, house here. There's another house. The pipe comes like this and then comes like this. You don't have to start drawing line from here and say everybody connect here. Yes, in reality, that's how it's going to be. Yes, but in calculation, I'll just come here and I create a node here. Listen to this. If this house, let's say that each of these houses are like what we did last week, are 3-bedroom. And the water, and so 3-bedroom, and we said 10 persons per house, and we say safety factor is 2, right? Therefore, and we say the water demand per capita per day is 100 liters per seconds, 100 liters per capita per day. We did all this last week. Therefore, the water requirement for a 3-bedroom house is now the value for one person, which is 100, multiplied by the number of persons, which is 10, multiplied by the safety factor, which is 2. And we are getting 2,000 liters per day. No more capita. Why? Because I've multiplied by 10. Then if you convert this, if you want to convert this to liter per second, because that is what we need for our pipe sizing, we remember that 1 day is the same thing as 24 hours, 60 minutes, 60 seconds, which will give you 8,400 seconds. Therefore, the water demand for this house, for this one house, becomes 2,000 divided 8,400, which will give you 0.0, right? 23 liters per seconds. And because there are 6 houses, right, it's now going to be 0.023 times 6. What's the value? Somebody can help us. 0.023 times 6 is giving me
0.139.
Now,
Okay.
I will now come here. I will say the water demand for this node is 0.138 liters per what? liters per second. So I don't need to come and start putting 0.23 here, 0.23 here, 0. No. Though in reality, like I said, in real life, everybody should connect. Everybody will connect. But in terms of design, you don't have to have all these multiple lines. You just come here, calculate all of them, and put the value here. Now, this is what confuses people, and this is where most of our engineers have issues. Listen now, watch me now. Very important. If this pipe continued, and then we now built new houses along here, this is where the 80% of people get confused in water distribution design, and this is the big deal now. Let's say another 2 houses. And this is their own node. Where if there are issues, I'll just go here and log off the pipe. If I'm doing maintenance along here, I'll just that's the essence. I'm coming to branch system and loop system. It's in your test. Many things are in your test. The test you have, gentlemen and ladies, is the curriculum of University of Stuttgart, their master's degree program. That's the semester program, and it's a practical thing. It's very practical. So just read it, you understand everything. Okay, now these are 6 houses. You'll agree with me, I don't need to do all this calculation again. One house is 0.23. Sorry. One house is 0.023 liters per second. All of them. So by the time you multiply by 6, like we did here, you will now get, here will now be 0.138 liters seconds. Stay with me. Now, if you notice, you discover that this man has 0.3, this man has 0.3. Automatically, here now, will now be the value of this place. You know, these people needed this 0.23, and this people needed this 0.23. It means that automatically, the value here will change to plus the value downstream, 0.138. So that becomes 0.276. So assuming that this place is called node C, let me call it node C, or Maho C, or Vav C, whatever you call it, or point C. And here is point B. Let me create another point. And then here is called point A. Watch me now. Now, are we learning something? Assuming tomorrow now, there's a new layout now, and we have another 6 houses. Remember, these are uniform, 3-bedroom bungalow. It could be more than that. It could be upstairs. It could be duplexes. Once it's duplexes, all you need to change is what is the population equivalent. And we'll still come to that. Or what is the land use? If you design a virgin place and you want to design the water recirculation system, there are no houses, right? The first question you ask is, what kind of houses are they going to have there? Are they duplexes? How many floors? That one is for pressure analysis. Then, but for the population equivalent, what is the population you want to expect? If you tell me we're going to have high-rise building, block of flats, and then I expect that 20 people will be in one flats, and they're going to be 200 flats. Then I'll just multiply and get the population equivalent. How many people need this water? Right? So assuming there are another 6 people here now, and the same value applies, which is 0.023 liter per second again. And it means this node here now is going to be, listen to this node here now, the value for this node will now be, will now be 0.136 for its own, for these 6 houses, but plus the value down, and that value down is 0.276. 0.276. That becomes 0.414 liters per second. Now I'm going to open the floor now for people to ask questions. I want everybody to grab this. If you don't grab this, you'll miss everything. And this is what a lot of engineers, a lot of consultants don't know how to do. This is their albatross. This is where the problem is. So I'm going to give you 2 minutes, 2 minutes. Somebody ask question. If you know you don't understand what I did now, please on your mic and ask me question. This thing I've done now, listen, before you say something, this thing I've done now is what we call the law of continuity. Listen, the law of continuity. In electrical, they call it Kirchhoff's law. As you are going downstream, the demand is increasing. It means that this person here cannot tell you that is even though there are only 6 houses, the default, what we call base demand, is 0.18. But the demand at that point is 0.141. Why? Because after it has taken 0.3138, it will release 0.276 for those downstream. When it gets here, the value becomes 0.276. That's the amount of water that should be flowing at that node. But him himself will only consume 0.138. It will release the remaining 0.138 for the next 6 houses to go. In that way, that is why as you are going down, the pipe sizes are reducing because the demand is going down. As you are going upwards towards the water tank, the pipe is increasing. That's why you see some houses where your neighbor is fetching water, your water will not run because the designer have not designed it to consider that after you have taken your own base requirement, your own water requirement, the excess water requirement will now go downstream and service those downstream. So now, you ask the question, sir.
Although the question I wanted to ask, you really answered it based on the pipe size at each node. As you go down there, what about the size of the node itself? Is it also applied to it?
No, the node is theoretical. Remember, this node is like a joining of a pipe. So it could be a reducer. So it's not consequential. It's just a reference point. Because this node too also carry pressure. This is where the surveyor point will also indicate. So that if you know the pressure here, you know the pressure here, you can know whether the pressure is adequate. Sorry?
Okay.
Please mute yourself. Okay. Any other question?
Yes, sir. Seems... From what I understand, like when you're designing this system, it's better to start from the downstream so that as you are coming up from and keep going up, you know the consumption from
the tank size. Yeah, you know the biggest tank size. Yeah.
Yes.
You will start at the lowest end. Then as you are going, the pipe is increasing, the demand is increasing until you now get to the final. That final will now give you the water demand for the whole system. But remember, sometimes you can also break them into zones, phases, branches, and what have you, which we are going to do now. So, gentlemen, if everybody understood this, then we need to go to...
hello, sir.
Hello.
Okay, ask.
Hello, sir.
Okay,
Yes,
I want to clarification on the node A. On the node A, is it the population increase that made this one, or was he included in the initial population before you start the calculation?
Okay, it is because this node A now, I demonstrated how the demand increases, pipe sizes increases. This node A has 6 houses connected to it, but then the pipe is continuous after him. You get the point? So if you ask me to design now it means here now, if I'm designing this tank now, at the end of the day, I will tell you that the water I need from here will now be 0.414 liters per second. If I convert it back to meter cube per day, that will give me my tank size.
Yes.
That's it. Now, assuming I eliminate this first section now, and the tank starts from point A here now, you will discover that the water demand will now be 0.276.
Yes.
So as you are going up, so the thing is, I mean, this is engineering. It's in mechanical engineering, it's in civil engineering, it's in, because of the law, in electrical, they call it Kirchhoff's law. As current is going down, the pipe size is, all of us know. You understand? You start with 25 mm armored cable or 50 mm armored cable. As it goes, passes the first street, the second street, it goes down, it goes to 25 mm. As it enters your house, it changes to 16 mm. As it goes to your DP, it sometimes changes to 10 mm, and so on and so forth, because the load is going off. In mechanical engineering, which is also civil, like here, which is fluid mechanics. As flow is going, is branching off, is giving out flow, the pipe size will keep going down. And that is how you get it, because the demand is keep going down too. Okay, let's go. Okay, somebody else has a question.
Yes, please.
Yeah, the lady, please.
So from node A to B is a pipe, and from B to C is a pipe.
Is a pipe with houses attached, to it, yes.
And we're trying to get the pipe sizes.
We're trying to get the water demand. Yes.
So that we can get the pipe sizes, which increases.
Yes.
As you're going towards the source.
It's increasing, yes.
Okay, thank you.
So from what we did last week, what is the pipe size? So for you to do a pipe size, you need the value for the slope. You need to know the slope of the ground. And from the German standard, which we are using, the maximum slope expected is 4%. If the slope is more than 4%, you assume 4%. This is engineering. The maximum slope in every pipe network is in your book.
Please, I have a little question to ask on this node A, please.
Okay, go ahead, please. Make it fast.
Yeah. Okay. At each node, we need 0.138 quantity of water to service the 6 numbers of houses.
Yes.
Okay. Now, from point A to B, we need 0.138. And from B to the other 6, we have 0.138, which gives us a total of 0.276.
At point B.
Okay.
You know, there are three streets or 3 catchments here.
Okay.
Catchment
I cannot.
Okay. B,
Okay. It's clear.
It's at the end.
Clear now. From the source, I didn't notice the houses from the source to point A. Okay.
That one is taking water from point A.
The houses from the source to point A is taking water directly from the source.
No, now it's taking water from point A. The first 6 houses are taking water from point A. The second houses are taking water from point B. Then the last 3 houses, 6 houses are taking water from point C.
It seems like they're taking
Okay, which means node A is servicing 12 branches.
No, 6. The first 6. But he must take care of the remaining 12 under him. So this first 6 we take 138. The remaining 12 are going to take 276. So automatically the requirement at point A is 0.4.
So I think the confusion there is a tank which links to node A, is where people are a little bit getting it wrong, which you have cleared that as you go down the stream, the pipe size reduces, meaning from the reservoir to node A is about 0.414 per second. From node A to node B is
well, okay, gentlemen, I'm sorry, my colleague, we don't have time. Let's go to the practical. Sometimes if you don't get something, by the time you demonstrate it will come back to you. You don't have time, please. I'm sorry about that.
Sorry, sir, just a little clarification on this noding.
Okay, ask it now.
The node, yes, is there going to be a reservoir to take water from the main reservoir and then distribute to the houses, or it's just a control point? That's what I want you to clarify.
I didn't get the question.
Can we locate where the source for this, so that people should understand the downstream and the upstream, the source, right, to be much more clear based on the historical explanation?
Now, when I started, I told us that the source is not too important, because the source is just, the source can be surface water, it can be groundwater, it can be, so this is the source. So here is pumping. Your pump will be here. Then this is your water plant. When I say source, okay, let me put the source. Water source. Okay, so
the water source
distribution.
Water source to treatment, then you now go.
If it's a treatment plant, it's also a source.
It is.
Water source to treatment plant.
Please mute yourself until when you are asking the question. Mute yourself, please.
Okay, I've seen the bar. I can mute them myself. Okay, everyone has muted. That was a good. Okay, gentlemen. Okay, so go back to branch system, please. We are kind of time constrained. Can you open chapter 8, somebody? Can I see your chapter 8? Can you open that chapter 8?
It's open, but we can't share.
I don't get you. Okay, so chapter 8. Can you see my screen? Can you see my screen?
Your screen is still loading.
Okay. Now.
Yeah, it's so.
There are two systems in water reticulation systems. We have what we call the branch system and we have the loop system. But I'll explain to you the difference between the loop and the branch system later. But today we'll be doing the branch system. From my experience, 80% of designs are branch system. Branch system has the advantage that it is easy to design. Let's say I don't know which layout to use as an example. Let's say your estate or your street, as water is coming in, one pipe will just flow along the main of the street. Then it will now be branching off street A, street B, street C. There will not be any connection to the street. And let me just demonstrate it with this. This is what a loop system look like. Just hold on. Okay. This is a branch system. Okay, let me go back to this. Lines, it becomes loop. If you add dotted lines, it becomes a loop system. If you remove the dotted lines, it will become like what you have in chapter 8, and that becomes a branch system. So you could see that the difference between a branch system and like 0.2 and 0.3, the difference is to put a dummy pipe. Dummy pipe. The reason of this loop system is that, let's assume there's a problem at node 2. Then I can supply water from node 4, so that the water can still go and get water. Because, for instance, look at node 7. If there's a problem, if I want to do maintenance at node, I want to do maintenance in a house between 6 and 13, I will just go to node 7 and turn it off. It will not affect any other person. But in a loop system, I can decide to not to turn off 7, but I will go to 6 and supply water from 2. So that is just the idea. But the disadvantage of a loop system is that it's very difficult to calculate because of if you're not careful with this pipe, it will fail. Assume you want to do the supply via alternative route. So generally, for now, let us focus on branch system and make life easy for ourselves. That's just what I want to say. So this is a typical branch system we want to calculate now, right? Now, to do a water design, you calculate the maximum water demand of the population, you calculate the maximum water demand of the industrial side, then you calculate the maximum water demand for fire. So there are 3 components. If you come to a place, the demand for residential area is known. The demand for industrial area, you need to calculate it. Then firefighting requirements. So these are the 3 components that make up your overall water demand. But if you are doing for a residential area, then there's no industry calculation. You forget about the industry. You forget about if you don't want to calculate for firefighting, you have a fire station somewhere and then their water is separate. All they need to do is to convey their water with their tank. They don't need to design that. And that's what we have in Nigeria. But in civilized societies, there will be hosts somewhere that will be designed in the network. That in the case of fire, you just go there, you open the host, take the host, and then you solve the fire issue. So here, the working step, the first working step is that step 1 says you work out the layout, which you have done. Is it a branch system? Is it a loop system? The second step is that you determine the elevation of pipes and the elevation of nodes. What are the elevation of pipe and what are the elevation of nodes? You have to determine that. And that's exactly what we have in this, our PDF, this sheet that I told us about. Okay, so this sheet will give you the parameters you need. And let me explain those parameters. The first column is the points, storage tank, 0.1, 0.2, 0.4, and point, all those points we have there. Then the second point is the elevation of that point. So for instance now, the third point is the length of the section. 0.1 to point, storage tank to 0.1 has a total of 120 meters length. 0.1 to 0.2 is 60 meters in length. 0.1 to 0.4 is 120 meters in length. 0.4 to 0.3 is 180 meters in length. Okay? This is 0.6 to 13. This is 0.7 to 11. This is 0.8 to 9. This is 0.9 to 12. This is 0.9 to 10. This is point. So you have to know the length of each section, which is automatically the length of the pipe. So that is column 3. Column 4 is the water demand requirement as per each node, which is point Z. And the points we have are storage tank, 0.1, 0.2, 0.4, 0.3, 0.5, 0.8, 0.7, 0.6, and this is how you have those points. This is point storage tank, 0.1, 0.2, 0.4, 0.8, 0.9, 0.10, 0.5, 0.7. So I want you to understand this thing about point and section. Remember last week, I said something very important, that to design any water reticulation system, you basically need 4 parameters. Those 4 parameters we said is that for the pipes, you need, number 1, you need the length of the pipe. You must know the length of each pipe. That's why you need a layout. You need a layout, you need a survey plan. And number 2, you need the diameter of the pipe, which is what you're looking for. If not, water will not flow. So the next one is you need the load parameters, all the load parameters. Another load parameters, you need the elevation. What is the elevation? A meter above sea level. And then what is the water demand or water flow? So this is, everything we're doing here is to determine these 4 parameters. And I told us last week that out of these 4 parameters, the surveyor, if you send surveyor to site, you already have 2. And those 2 you have is the length and the elevation. Every surveyor that goes to site and come back will list out the length of each section. And those length of section, that is what you put in Excel. As I indicated, you must put it in Excel and it will look this way. You put in Excel, so it will look this way. So those lengths that they call out from the surveyor, you put it here. Then the next parameter the surveyor will give you is the elevation at each point. That is what you have here at column number. At column number here, elevation of point Z. Remember, this is the elevation from the surveyor, from the plan. Look at the plan again, the contour line. You see, this is the plan. Then this is the length.
Oh, the instructor is gone again.
Please, is there any question as regards these charts? I don't think there's any question. So the 2 parameters, once you put these charts, you now bring out the 2 parameters from the surveyor. So the elevation, or you call it out. I can call it them out. If you're looking at AutoCAD drawing, you can be seeing the nodes, the survey plan, you can be seeing the elevation, the spot height. Then you can now use your mouse, your distance tool in your Excel, in AutoCAD or whatever, or ask the surveyor to write out distances. You can do it. Sometimes this point A and point Z will be 3.31 something. It will be the XY coordinates. It doesn't matter. It could be the XY coordinates. So these 2 columns could be the XY coordinates and then the length between one coordinate and the other one, whatever parameter it is. But it is good for you to number it this way if it's a small design, so that you can be able to name every pipe. So if the pipes are changing, you say pipe 2 is 100 mm, pipe 3 is 150, pipe 4 is, that kind of thing. So it's good you name it. Even though it comes in terms of point this to point this, it's good that you name it to make it look sense. Remember, as I said, this is a standard international design. This is how it is done, irrespective of any country. Okay, so with these 2 parameters in place, you now need to find out the other 2 parameters. And those 2 parameters are now the liter per second, which is the water demand, which you need the slope. Column 4 is talking about the slope. Are we together?
Yes.
Good. Then column 5 is now the diameter. After column 5, forget about the rest. The rest is what we call check. I'll tell you about it when I do the design. This 1, 2, 3 is check. Is an academic work. What you need is just 4. So in your real practical consultant, what you need is not more than 6 columns. No more than 6. This one is to check. This is like elevation real, slope real. This is slope. This thing is I mean slope, which is 1,000. This sign means diameter in mm. This one now means real, because if you remember last week when we were doing using monogram, you might not get the exact slope you need. You might not get the exact pipe you need. You use closest pipe. And when you get this closest pipe, you can go back and recalculate the actual slope. We will still come to that. Then you can now go back and calculate the actual losses, the velocity. We'll still come to that. So now the surveyor has given us 2 parameters, the node and the distance. Our job is to get the other 2 parameters, which is the liter per seconds and the diameter. So that is where we are now. Any question?
Sorry, my question is, this value we have in is it the difference between 2 nodes or just one? Because I didn't see.
Yeah, is it different between you mean the distance, right?
Yes, the distance is clear, but the elevation we're seeing, is it the difference?
It's not difference, it's the spot height, is the exact location of that place.
Okay, between one node to the other. Now, like you say, starting, which is ST and 1, distance is 120. And I'm now seeing
at point Z, it's showing the elevation at point Z.
At point Z.
Sorry, I'm not getting. Okay, elevation at point Z.
Z means height. Elevation.
All right. So this elevation, is it like you said, ST and 1? Which elevation? Is it the difference in the 2 elevations or elevation at 1 point? Because I'm only seeing 1 value.
At only that point Z, the second column, at the second column, not average. So
I think we are not getting him right. He is referring to elevation of point Z. As we compare that of the points X and point Z, we refer storage point and point 1, and we say it's 120. This one for the elevation, where are we comparing the elevation? 310, 290, 79, 272. Is it elevation of different nodes? I think that is what he's asking.
I think it's from the topography.
No.
Point Z.
Get it clear. Get it clear. What we are driving at. Excuse me. What we are driving at for you to design what you drive at is the difference in elevation, so that you can be able to get your slope. Now we're only having 1 value. I'm saying this 1 value we have, is it on 1 node?
Okay, hold on.
It is on the second column.
Okay, everybody, hold on. Just hold on. This elevation is only 1. It's point Z, and it is the second column. The elevation of point storage tank is 310. Check the map. Elevation of point 1 is 279. Elevation of point is 272. Elevation of point 3 265. Listen, hold on. So, but when you want to do the distance is now 2 sections. The distance between 2 sections. And for section ST to 1, the distance is 120. Section 1 to 2 is 60 meters. Section 1 to 4 is 120 meters. Section 4 to 3 is 180 meters. Section 4 to 5 is 120 meters. But elevation of section ST, storage tank, is 310. And that is the highest point. Elevation. of,
sir,
you
I
have
want
to
to
understand it this way, sir. Elevation of point 10, which is the last one, is 260. So you
It's
call
clear.
it.
It's all right. It's clear. So with that, we can be doing the difference in elevation and get as low. It's clear. Very
No,
much clear.
no, sir. No, sir. Yes, you'll be getting the difference here. You're right.
Yeah, I'm right. That's it now. Because at this point,
there's
now,
another
this is the
difference you
elevation.
can do on site, sir. I was saying that the surveyor might not give you 0.1 or 0.2. He will give you the elevation here, the elevation here. You will now mark out the map, the distance between those elevations, right? Let me not digress. It will confuse some of you.
Sir, I want to ask a little question. Can we use this elevation and calculate the distance between two different nodes, just like from the storage to
thank you. No, the surveyor must give you the elevation of point storage tank, elevation of point 1. The horizontal distance between them gives you the distance. But point 1 has only one value elevation, has only one elevation.
It's clear.
It's clear.
Okay.
You can go out, sir. Okay.
Okay. Now, can you see my screen? So these are the steps. So step 2 says determine the length of pipe, elevation of load. Do we have it? We have it. Now go to step 3. Step 3 is draw the network. Is he understood? Well understood. Step 3 now says you determine the flow rate. I've shown us how to determine the flow rate, right? By total population. Thank you. Now, what this place is telling you is say that if you're not giving number, I give houses. Sometimes you're not giving houses, you're giving area. All you do is you calculate the total area, and you use what we call land use. And you calculate the total population. Now, what we mean by that is this. Here now, if I have a land like this, and I have another land like this. This is not house now. This is
Engineer Uche. I think you may need to plug in your power. I think your battery is really running low.
Okay, let's continue. All right, let me multitask. So this is the 2 lands, and one pipe need to come here, another pipe need to come here. Then they meet at a node, and then they go to another land upstream. And you are told that this land is 10. All is not.
1,000.
10 hectares.
I've already given.
Please mute yourself. And this one is 20 hectares. Watch me now. This is where engineers fail it again. Then they told you that we have high density area. Let's say they tell you it's 800 PE per hectare. And you have medium density. I'm just making an assumption. There's a book on that. They say medium density is 500 PE. That's population equivalent per hectare. Then they say low density is 200 people. Gentlemen, we're all engineers. If they say 200 PE per hectare, all of us, now I'm digressing now just to make it make sense. All of us know that 1 hectare is equal to 10,000 square meters. This is not part of what I'm teaching you. I just want to digress so everybody will be on the same page. 10,000 square meters. It means this is 10 plots. 10 plots. Stay with me. This is 10 plots. At 1,000 square meter per plot. Yeah? You get it? So if you are buying 1 hectare in Abuja, you want to do something, and they said, how many plots of land of 1,000? It's 10 plots. If it's 500 square meters, 50 plots. It's understandable. Now, if they say it's 200 people, so it means any house you're going to build here will automatically be 200 divided by 10. That means we're expecting 20 people in the house. This is how the environment control and development authorities calculate high density, medium density, low density. So if I now say 20 hectares, and they told me that this plot is being designed as a high density area, then what is the population equivalent? Remember, to get your water demand, you just need the population equivalent. We already have a standard that for residential areas, 100 liters per capita per day is in your test. For hospital, 200 liters, each patient requires 200 liters per capita per day. A school needs only 10 liters per capita per day. Or they say 10 liters per student per day. Because 10 liters means you only go to the toilet, you drink water, that's all. For residential area is 100, and so on and so forth. Did you get it? Where are we? Okay, so now, these 20 hectares now automatically means if it's a high density area, you just say 20 times 800. So, and that will be what? 16,000. So for a 20 hectare land, you are designing for 16,000 persons. Therefore, the water demand going to this hectare of land will now be 16,000 times 100, which is requirement for the person, times 2, which is our safety factor. So what you have here is 32,000,000,000. And that gives you, that's in liters per day. But you know, as the value is too much, you convert it to meter cube, which is 32 meter cube per day. So that means to design for 20 hectares land, what you need is about 200 liters per day. Then you now convert it to liter per second. It will give you 3200 divide A6400. And that gives you 3200 divide A6400. That will give you 0.0. Am I sure of this? Yes, 0.037 liters per second. So this is the amount of water you need to flow. Are you sure something is not wrong here?
I think it should be meter cube. We have converted to meter cube instead of.
We are converted to, thank you. So this is 000. So multiply by 1,000. How can you use 37 liters per second? You get it? As a designer, do I need to calculate for this one? The answer is no. As long as it's the same residential area, I'll just say 37 divided by 2. This is 10, this is 20, right? So do you see, there are no houses, but I've calculated it. Based on the assignment I gave us, which is what I asked us to do, those values that they got, that I asked you to design the pipe sizes, this is how they got them. Very simple. So let us go to monogram and quickly design this, so that let's know we have taken something home. You now go to your monogram. And then let's assume that the slope here is 0.5% slope. That means I have measured between this point, between the point of supporter source and the last point here, and it's giving me a loss of 0.5 meters, 50 cm for every 100 meters, which is fair. Okay? You remember that? Those who attended last week. You know how
is it meter or in kilometer?
That's a good question. This is not kilometer. It says 0/00. So this is meter. This is by 100. If I write it 0/00, that's a good question. If I write 0.5, then I now put like in our chart, I put
over 0.00.
Yeah, I cannot get the second zero, but let me try. This is per mil. Per mil, sorry, per kilometer, per kilo.
Excuse me, sorry, sir, to draw you back. I'm just looking at this calculation you made about this one is 10 hectares and 20 hectares. For 20 hectares, you got 16,000 people equivalent. Then I was thinking that for 10 hectares, you should have more people equivalent. But what we have here is 20 people. I don't know if I'm wrong. So I'm just looking at it.
No. What we did here is that, no, you were wrong. This is 20 hectares. We got 37 liters per second. We got 16,000 equivalent.
No.
So this
I'm
one is
talking about the
8,000.
people. I'm talking about the people equivalent, not about the liters. The people equivalent for 20 hectares.
10,000 is 8,000. 10,000 is 8,000.
Is how many, sir?
8,000.
8,000 people.
20 hectares will contain more persons than 10,000.
So what about these 20 people down here? What is this? What does this signify?
This is for a 1 hectare now. Okay, I see your confusion. This one is for 1 hectare. It's for 1 hectare. It's for 1 hectare. That's a good one. Yeah, no, it's a good observation.
It's for one hectare. Yeah. Thank you.
That is for 1 hectare, please. And not just 1 hectare, at low density too. We assume low density.
Yeah, at low density. Thank you.
Yes, that's a good one. Understood? So now I just wanted to finish up this. So somebody go to your monogram, open your monogram. Let us design these 2 pipes. Let us get the size of these 2 pipes. If that is what somebody gets today, I think is still worth it. For especially those who don't really come last week. Those who came last week, you already know how to do pipe sizing. I'm still coming to that assignment. So there are 3 pipe sizes, like we said: PVC pipe, ductile iron, and concrete pipe or asbestos, which has been banned. So monogram of 1.00 has a higher frequency than 0.4. So open the monogram for 0.1, which is PVC, PPP, or PVC pipe.
You haven't finished explaining the 0.5% per.
What of HDPE pipe? How do we also size that one?
Upstairs.
PVC pipe.
Last week you said that PVC pipe is very smooth. So there are 3 monograms. Like I also said in the WhatsApp group, you can go you see many charts online. But the one I have for my university is they calibrated for PVC pipe, ductile iron. A ductile iron is 0.4, concrete pipe because it's rougher. It's rougher. Those things are frictional factor, or if Manning's end or dashes ratio, whatever. No, we'll still come to that. Many of us have not read that test. Many of us have not read our notes. That's just the point. What I can understand.
You have not finished explaining up there 0.5%.
Okay, so I said when you see, like in your chart, when you see 0/00, it means per kilometer. When you see 0/0, which is percent, is per meter. Remember, meter is 100, kilometer is 1,000. So it's not there is per hectare. When I say per hectare, it means per 10,000. When I say per kilo or per mil, it means per 1,000. When I say percent or per meter, it means per 100. So I mean, it's understandable. I think when I say per deca, it means per 100,000 or so, but we're not into that. Per hectare is also, I think, it has its own reference. So if you go to our monogram now, have we opened the monogram?
Yes. My mass is hovering around more than 300 diameter, close to 400 diameter, if I'm correct.
Are you with me? Are we together?
Yes, sir.
Now, if you look at this chart now, on the horizontal is your liter per second.
We are not seeing your chart, sir.
Oh, okay. Yeah, still on my whiteboard. On the horizontal is your flow in liters per second. So as it gets bigger, it goes into meter cube per second. You know what? So this is 2,000 meter cube per second. This is 3,000. This is 4,000. This is 5,000. This is 1 liter per second. This is 2. This is 3. This is 4. This is 5. This is 6. This is 7. This is 8. This is 9. This is 10 liter per second. Then from 10 move to 20, 30, and so on and so forth. The rule says that anything less than 1 liter per second, you assume the value for 1 liter per second. Let me say it again. You know, those of us are civil engineers. You cannot design a column with less than 16 mm. You cannot space your reinforcements more than 300 mm. So that's what we call limiting values. In every design, there's always what we call limiting values. Even if the thing will not carry anything, this is the minimum you can use. So in this case, even if the flow is 0.8, you just assume the 1 for 1. Even if the 0 is 0.2 flow, you use the value for 1. And that is what this chart is saying. So 1 is the limit. And then the same thing applies to slope. If the slope is less than 0.1 per thousand, this slope is calibrated in per thousand. That's why it's 0.00. This is per kilometer. So if I say 2, slope of 2, it means 2 meters per kilometer. 2 meters per kilometer. Or if I say 2%, it means 2 per 100. So,
sorry, is it 2 cm per 100? You bring it, remove it.
Depends on the reference you use. Slope has no ratio, has no units. Because slope is a value of vertical over horizontal, meter over meter. So it has no ratio, it has no unit, sorry. It is comparing 2 units. So if I'm measuring and I say 2 per kilometer means 1,000 meters. So I'm saying 2 over 1,000. I'm losing 2 meters over 1,000 meters. I'm losing 2. If the value is percentage over 100 meters, I mean, we're all engineers, we don't all know that. So now let's just calculate for those 2 pipes. The first pipe is 37 liters per second. You now come to this pipe. You now come to this pipe and you look for 37. And we say the slope is 5%. 0.5%.
0.5.
That means in our chart, 0.5 means 5. Understood? Because we are doing 50,000.
Yes.
So I'll now come to 0.37 now. Or let me, for the purpose of this training, let me assume it's 40. I'll come here and I'll read it, and I'll look it for where it hits 5. And the value is 200. So can somebody confirm? 200 diameter. And when I hit this 200 diameter, somewhere here, this is 5. It's falling between 2 lines, moving from left to right. Those 2 lines is 150 and 200. It's also falling between 2 lines, moving from right from left to right on the downward side. And that is 1.2 and 1.0. This is the velocity. Those are here last week. I said that as a simple principle of design, your velocity should not be less than 0.3 and it should not be more than 3. That is the standard. The velocity should not be less than 0.3 liter per second, the speed of water flow. And it should not be more than 3. If it's too low, it's a problem. If it's too high, it's a problem. So once I read this, and I got and I got to 2 pipe size, I will receive 2 parameters from this. If you check, you will see that it's between this pipe and this pipe. I will choose the biggest, which is 200 mm. It means I need 200 mm to supply water to a 200 hectare estate or 200 hectare, 20 hectare district. And that is my primary pipe. When we start going down, those primary pipe will now start going small again.
Sir, I'm a little bit lost in the use of this chart to do the design. Please repeat a little, please.
What do you want me to design to repeat, sir?
More especially how you trace that of the slope side, which is the vertical part of the chart. I understand the horizontal, which is the liter per second. I understand it. This value of V, which is velocity, whatever, I do not understand. The size of the pipe, I understand. That of the vertical,
okay, just hold on. When I trace this pipe, it ended me somewhere here. It almost landed me in somewhere here. And it was 2 lines, 2. 1, 2, 1, 2. Are you seeing my screen? 1, 2. So I will choose the last one. This is 1.0. It's written 10 there, but if you print it out, you see it's 1.0. So it means that if the velocity is okay, and the pipe size is 200 mm, the same way you saw 2 pipes, the same way there are 2 lines. It is just like a psychometric chart. Mechanical engineers will know this more than civil engineers. So, did you understand it now?
Okay.
Hello, sir.
It will fall between 2 pipes. You check whether the slope requirement, the velocity requirement is met. Then moving from right to left on the upper side, facing up, it will also fall between 2 pipes. You choose the biggest one, or you choose the biggest one. Because last week I told you that it's better to over-design than to under-design.
Okay.
Excuse me, sir. Hello, sir. Yes, if you look at our graph, the chart, we're saying the maximum is 3 and the minimum is 0.3. Is that what you say, sir?
Yes.
Okay, like from the assignment we have last week, although I know we have not handled that, but there were cases that when you are tracing this chart, you have a value that is maybe parallel along the vertical, and that is to say it doesn't intercept with any the horizontal. How do you handle such situation?
It's not intercepting, it will fall between anywhere. You now choose which one, like, I don't know how to explain it to you. Any value that does not fall within this place, you use empirical value. If you are dealing with flow, or you are dealing with any pipe size that is more than 1.1, 1.2 meter in diameter, it means you use empirical. So it means this like chart is limited to 1.2 meter diameter pipe.
Like what I'm saying, actually.
Abuja was designed with 1.5 from the mains, but as it start going down, it start going to 1.2.
Like the assignment you gave us last week. Sorry, sir. The assignment you gave us last week. No, like camping. Sir?
Yeah, what
like
did you get?
Camping, for example, when you calculate the volume for the camping, you discover that you have less than the 40 mm diameter that is there on the chart.
I said anything that's less than 1 liter per second, you use the value for 1 meter per second. It means 40 mm is the minimum you can use.
Okay.
any value that is less than, how do I put it? Are you a civil engineer? If you're a civil engineer, you will discover that you cannot use 12 mm to do column. You cannot, because there's a 13% reinforcement requirement for a column. I don't know how to put it, based on BS 8110. So for
that's
every design,
minimum reinforcement.
Minimum reinforcement. So for every design, 20%. Like in sewage, in sewer design, when we start sewer design in 4 weeks time, sewer design says that you cannot use any pipe less than 6 inches, 150 mm, to do your sewer design. Well, based on German standard anyway. You cannot. So if you see anybody laying sewer pipe with 4 mm, 4 inches, 100 mm or whatever, 4 inches, it is absolutely wrong. You can use it in service building, in building services. But in terms of, you know what I mean, in terms of centralized wastewater water plants, centralized network, you don't use that. The standard also says that you must put manhole between 60 meters, not more than 120 meters. Nobody's doing that one anyway. You cannot go more than 190 to, you cannot go more than 120 meters without having a manhole in a network. So these are like rule of thumbs. Yes, that's the word. These are like standard rule of thumbs. And last week I told you some people something. I said if you are doing infrastructure design, I have seen many people using 50 mm, which is what you are saying now. I said as somebody I've seen things, don't use anything less than 75 mm. It's a rule of thumb I'm giving you, and it has justification. Even though you can see 50 mm as the minimum you can use, but please make sure you don't use less than 25 mm in Nigerian case. Any other question?
Okay. Can you hear me? Can you hear me?
Let's move to the branch, the branch one. No.
Okay. Yeah, I want to ask, because I listened to the recorded record from last week, in which it said that the slope we are using is actually the highest point from the catchment area, with the explanation that, okay, if you are able to actually supply water to the highest point, then the lowest is actually meter 4. Is that correct?
That is
so
for sizing.
Okay,
no, sorry, hold on. That slope is for sizing your entire network. Listen now, your network requires a certain pressure to exist in the system. And we say that the maximum pressure expected is that must not be exceeded. It's 8 bars. And we also say that the average, the acceptable pressure within your network should be 2 to 3 bars. Acceptable, maximum. So if you are sizing your tank, where do I locate my tank? And how do I know how high the tank should be? You now take the elevation of the highest point and the lowest point. If it does not meet your pressure requirement, you elevate the tank to the level that will give you that pressure. If you don't elevate the tank, the water will not flow. And then you also know whether the choice of the elevated place is adequate or not. I told you about they did a different plant in Mango. They now located the highest point at a distance of 10 kilometers. So it means from the dam, they will pump water to the highest point first, 10 kilometers. Then the water will flow down via gravity. That's point and energy. So that is what it is. But if I'm trying to size my pipe from your house at a distance of 100 meters to my house, I will take the slope between your house and my house. That becomes the slope for me to design the pipe, because the slope from your house to another house or to the tank has already been determined. So I'll just take the one from my own, from your own. Is it understood?
Well, I'm trying to get your illustration, but it's not. So this 5% now, looking at 20 hectares, now looking at the table 1, whereby we have the maximum elevations to the 310 for where we have our tank, and we have the lowest one, and we still have the other point. So this 5% now is for which point? If we can just use that illustration from the table.
Okay. This 5% now is from the tank into the estate, into the district. From the tank, from the supplying tank to the district. You get the point? This is just primary tank, primary pipe. Now you now start designing the secondary pipe. That is where this thing I'm talking now comes in. The small 3 foot trees.
Okay, sir, it's understandable now.
We said that this one is the most important thing. Listen to me. I've designed the design for what they just designed is the treatment plant. That's all. Once you can get that one right, the other ones we are going to do them. The other ones is now the small things you now do. The one going to Ladoke Akintola Street, the one going to this street, the one going to Alaji. Those ones 150, 150 mm, 200 mm, 100 mm. But the main coming, which is now this 200 mm, if you make a mistake and you use 200 mm here, everything is rubbish.
That side should be 250 from our case study.
Okay.
250 from our case study.
Exactly. That's where I'm confused because my mass is falling within 200 and 250.
No, it should be 250. If I between 200 and if I between 200 and 250, you say we should use the bigger pipe.
It's closer to 200, sir. If me, I'll use 200, sir.
But for your structure,
if you use 40,
if you use 50, 5.0. If you trace it horizontally, 37 from below now down to 5.0, which is 5.0. Exactly. If we're between 200 and 250, you say we should choose. Sorry, we should choose 250. Yes,
choose 250. Yeah, choose 250, sir.
Yes.
Okay, please choose 250. You're right. Let's get me the one for the 10 hectares. Everybody, in 1 minute. What is the value for the 10 hectares?
Yeah.
18.5 liters per second.
Yeah, the same. Yeah, it's a flat land.
We calculated it to be 18.5 liters per second. The volume.
What's the pipe size? The same slope is 5% slope. Remember, if I didn't say 5%,
that's 200 mm.
Let me say something. If I didn't want to say 5%, I'll tell you it is 0.005. 0.005 is same than 5%. True or false?
True.
Okay. So what value do you have? What size of pipe?
It's between 150
200.
to 200, but it's close to 150.
I said it's 200.
It's closer to 150. Very, very close.
Closer to 150.
Okay. Assuming there's another estate that is
200 mm.
That is has 6 liters per second, and the slope is 0.05. Listen to me. The slope is 0.05. The slope is 0.05. The slope is 0.05. And the water demand, the water requirements, 0.05 is the slope. And the water demand is 5 liters per second. What's the pipe size? The slope is 0.05. I didn't put percent. 0.05.
The pipe size is
125.
100.
Okay.
125 mm.
100 mm. 100 mm diameter.
100.
Okay, 100.
It was exactly 100.
125.
125.
125.
It's closer to 100.
Use 125.
But now this is where your wisdom as engineer comes in. If it's too close to 100, Kai, to save money for the client, you use 100 because you already factored in factor of safety.
Of course.
And then if 125 is not in the market too, I don't think we have 125 in the market. All we have is 100 and 150. So you use 100. It will flow. Because I've already doubled Yes.
So that's why it comes to that chart. What is real, obtainable in the market?
Yes. So you now come here and fill those values. So
I didn't
let's go
get
back
it
to our
though.
chart. Sorry?
I didn't get it. You said the flow is 5 liters per second.
Yes. You read it against 5.
And the slope is 0.05.
I tried to confuse you guys, but I withdrew it. When I say 0.005, I expected to multiply by 100 to be 0.5, multiply by 110 to come back to 5. You get the point? When I say 0.005, I didn't give units. But the other one, I gave you units. So all you need to do is multiply by 100. But this one, in this case, you multiply by 1,000. So 0.005, you multiply by 1,000 to still come back to 5. So you read it against 5.
And everybody should note that confirm that your chart is 1,000, so that when you hear 0.0,
now, if you download any chart, that's not my chart. That's not our chart. The chart will tell you chart rules. Every chart has its own rules. So you just read the chart rules.
Hello, sir.
Yes.
So for the 10 hectares now, so what value do we take now?
The highest one.
Well, it's close to 150, not 100.
You take 150. Was it 150 or 125?
150.
No, it's 150 because 150 is even for 20 liters per second. And meanwhile, our value is 18.
18. We have 18.5.
Yeah, so 150 diameter is, yeah.
I think we all got it. So let's move on. Those small things that doesn't. I'm happy everybody got it. So let's go back to our design now. So this is our design. So we are starting now. So the first thing you do is you fill this chart. You fill this place. You fill the diameter. So to fill it, I think there's something I call ABC design. Can you go back to your drive? Can you go to your drive? ABC design. Can you download it? ABC estate design. Okay. Are you there? Are you there?
Yes.
Yes, sir.
Okay. So now we are assuming that each of those dots in those houses are 3-bedroom houses, are bungalows. And we are also assuming that each of those houses contain 10 people. This is relative. Now, this example, and we are assuming that each house is in the street. Now, this is general assumption. Has, okay, this is an example in intro and assumption. Let's assuming that each house has 10 houses and each street has 30 houses. And there are about 50 streets in the estate. This is like a question to trickle your attention. The question now says, what is the water demand per house? What is the water size per street? Are you with me? So 30 houses per street, 50 streets are in the estate, in that our 20-hectare estate. The question now says, what is the water demand per house? So let's solve the first question. So here, assumption. Am I sure you're seeing my screen? Yes. It's very important that you make sure you are muted all time. I'm muting some people and they're muting themselves. So 10 houses per house is the population. We call it 10. We're using a peak factor or call it safety factor of 2. And we are assuming a slope. We are assuming a slope of 0.5. And we also assume that the specific water demand are 10, 100 liters per capita per day. All these things are reasonable assumptions. You know, one thing I have learned in consultancy is that a consultant is smart and wise enough to make reasonable assumptions. You must make assumptions. You must make, sometimes they might give you a layout. They'll just tell you, design the water recirculation system. You tell them how many floors of buildings are there. They say they don't know. You can assume 2 floors or 4 floors. If that person now decides to change the design to 5 floors, you, the consultant, will say, look, I designed this thing for 4 floors based on the elevation of the tank. If you build a 5 or 6 floor building, that means you are going to build a new tank for it, or you improvise tank on building, that kind of thing. Now, let's answer question 1. Okay, these are all assumptions, right? One day, this, one or this. So first question. What is the water demand? The water demand is now for a 3-bedroom using the equation we all know. Becomes 100 times 2 times 10. That gives you 2,000 liters. Well, we've done this. Any question? No question. So this is the answer. So for each of the streets, what is the water demand that will go for each of the streets? Each of the streets is 30 houses. It means if each house is 10 and there are 30 houses in the streets, automatically means you are designing for 300 persons. So the easiest thing to do is just to multiply 300 times 100 times 2. That will give you 60,000 liters per day. And you convert it, it will give you 0.69. And I said use 1 liter per second. You now go to the slope, to the graph, and you read it. It will give you between 50 and 65. And I said choose the bigger of the 2, or the one that is available in the market.
You said we should choose 75.
Yeah, in practical, yes. 65, you can't see 65 pipe in Nigeria. 75 pipe is 20 inches, it's everywhere. Question 3, question 3 says, what is the water demand and pipe size of the main pipe? Main pipe or primary pipe? That means there are 50 streets in the estate. Each street has 30 houses. Now we go to last question. We just multiply 50 times 30 times 10. And that will give you what? 15,000 people. That means this estate contains 15,000 people. So you go back to your design and design this, and it will give you 34. If you remember, we just finished a design now that gave us 37. Gentlemen, I cannot go back and start reading the chart again. I will assume 250. Okay, let's read. Maybe to give us 200, we'll save money for the client. So I go here, 34. 34 against 0.5. 200 mm. Somebody confirm. Confirm that it is 200 mm.
Yes, sir.
It is.
So you can see that if I'm asked to design a water reticulation for a district, a village, a state, whatever, of 15,000 population equivalents, which is if you break it down, it's like 50 houses, 50 streets, with each street 30 houses. You know that kind of thing, right? So you have to choose how you derive your population equivalent. All I want is your population equivalent. Population equivalent, if you multiply by the requirement of one person, to give you and multiply by 60 factor, you give you the water demand of that place. So in this case now, the water demand is 15,000, and because it's 15,000, you now calculate it to be 34 liters per second. You will now choose a pipe size of 200 mm pipe, which is 8 inches. So 8 inches pipe is what you should bring water into the estate. After that, you now start designing the street. Can somebody calculate me the pipe size for each street? What will be the pipe size for each street? Do you remember? The entire estate is 50 streets, but each street has 30 houses. So what is the pipe size that will tap up from the main? Can we quickly do that? Get that how you post it for me. One liter per second. What's the pipe size? Should be 65, right? 65.
Correct, it should be 65.
So that is why I now gave you that advice, asking you to use 75 mm. I get, as a consultant, if I get 65, I use 75. Because 75 means if tomorrow they decide to build more houses in that street to 40 houses, my pipe will still be adequate. Is that understood?
So I have a question.
Yes, it is, but
I have a question.
Go ahead, please. We don't have time.
So now, in considering that every street we have assumed that it is 1 liter per second. So, but if it is building up, let me say from downstream, it is building up. Does it mean those other streets are more than 1 liter per second? Other streets in an estate.
Okay, let me answer you very fast. Let me answer you fast. I want you guys to give me the value for 5 streets following one of the streets. 5 streets following one of the streets. What will be the value of the pipe? 5 streets, 5. Quickly do it. You know what I mean by 5 streets now. Assuming this is streets. You now go like this, go like this, go like this, go like this, go like this. And then go like this. So let's say this is street A, street B, street C, street D, street what now? E. So it's more now. So F. This will be street what now? F, G, E, F, G. How many streets now? 1, 2, 3, 7 streets. What is the value of 7 streets? Calculate. What is, what is the pipe size of this? What pipe size should be here? Which is like asking you, what is value of 7 streets put together? Can we quickly do that one?
So
what do you do?
Yeah, so if I'm correct, I think we get
7 times 0.69. Yeah. That's just the value.
69. Yeah, that's 4.83.
4.83. I go to chart. 4.83 at 5%. What do you have? What is the pipe size?
That's
4.83 is as good as 5.
100 mm diameter. 100 mm diameter.
Thank you, sir. So do you understand it now?
Okay, yeah, I understand. I'm clarified now. That means you do the actually. I feel. Yeah.
Like I said, this is the crux of the training. This thing you understand. Even me, when I did this course 20 years ago, in far away that I didn't understand it. But when I now came and started doing this training, I now discovered that this is where people fail it. This is just a problem of engineers here. You will see somebody now. Do you know what they will do? 50 mm, 50 mm, 50 mm, 50 mm, 50 mm. Rubbish. I mean, that's not what it is. If you go further, the only pipe that might carry 50 mm might be these last two. Probably this one will carry 75, 75, 75, 100, 100. But if you got this 100, forget it, you're okay. Because it is possible that this street has not been developed, this one has not been developed, but the land use has been given to you, and the layout has been given to you for the town plan or the architect. So once you get the main correctly, forget the rest. Like I said, when they design Abuja, they didn't even design all these primary and tertiary lines. What they just design is the main. Somebody want me. Any question?
So, okay, how do I use the charts to do a reverse engineering? Suppose I go to an estate and saw a pipe with a specific diameter. So how will I use the charts? I said if I go to
if you get the layout now. Okay, to answer your question, let's quickly rush through our training. Everybody, bring out your bureau and pen. We are stopping this class in the next 20 minutes. Bring out your pen and bureau. I want you to count how many houses are between 6 and 13. Each house is 0.023. How many houses are between 6 and 13? Multiply by 0.023 and put the value at node 13. Okay, so let me clear this. So let's start. Node 13. What is node 13? Node 13.
What drawing are you referring to, please?
This our main exercise, this one.
Okay.
What is node 13? We'll make an assumption. Assume 20 houses. I'll be mentioning numbers. Just assume 20 houses. So what value is node 13? The value in node 13 should be the value in node 13. Sorry. The value in node 13 will now be 20 houses. Times the value of one house is what?
0.69.
No, sir. 0.023. Remember, we say bungalow.
Okay.
0.69 is for 30 houses. Remember, and it's a different thing now. We're entering a new thing now. What did you get? What's the value? .46.
0.46.
Good. So you now go to node 13 and write 0.46 liter per second. Now move to node 6. How many houses are connected to node 6? How many houses are here from 6 to 7? I'll count it for you. 1, 2, 3, 4. Here is empty land, but I will assume another 4. 1, 2, 3, 4. So 8 houses are connected to node 6. 8 houses are connected to node 6. Therefore, node 6. Node 6 is now node 6 is now 8 times 0.023.
0.184.
0.184. However, node 6 is node 6 or node 13 plus 0.184 will now give you what? 0.46 plus 0.184. Did you see this?
0.65, 0.64.
You now go to your table. Listen, you now go here. Node 6, look at node 6. You come here and you write 0.65 here. So what we are going to do next week is that everybody is going to print this, print hard copy. So we'll fill this number. We have learned how to fill them today. Next week we'll fill them and then we now use our computer application. Do you get the point? Within the week, I'll tell you things to print. This is online training. I'll give you sheets to print, one exercise to computer application to print, because reading on screen can be difficult for some of us. So please find time and print it. Hold it in your hand. Node 13 is 0.18. 0.1. Okay, let's go back. Did you understand this? Let's do node 11.
Please showcase the short it and say.
Let's go to node 11. Node 11 has 10 houses. Therefore, the value will be 0.023 times 10, which will give you 0.23. There is no downstream line, so that is the value of node 11. Then node 7 is now node 6 plus node 11. Any question? Node 7 is now node 6 plus node 11. Go back to your layout and ask me, tell me whether you understand it or not.
Understood? Yes.
Hello, sir.
Why did you consider only node 6 and 11 to get node 7, and you did not include node 8 that is close to it?
Is it, sorry?
I mean, the node 7. You said node 7 is node 6 plus node 11.
Node 7 is node 6 plus node 11. What do you
It
say?
should be node 6 plus 11 plus 4 houses. There are still 4 houses you didn't consider.
Oh.
So I'm saying, what of node 8 that's close to it?
7. Yeah. Okay. I'm not even looking at this now. I was just assuming that I already know.
Hello, sir. Hello, Engineer.
Yeah, can you? Wait.
So
Let me
can
check.
you just pick one of the nodes as give example, show on the chart how you are counting the houses.
Okay. This is node 11. 1, 2, 3.
I can't see your screen.
Sorry.
Display your screen, sir.
This is just an assumption. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's 10 houses. This one I assume 20. I mean, this assumption, gentlemen, it doesn't matter anything. No, not like accuracy in engineering. 1, 2, 3, 4, 5, 6, 8. If you design for 20 houses or 25 houses, is it consideration?
Can you point node 7 on that contour map?
This is node 7 here, of course. Now it's here now.
Now,
I said next week.
Upstream, after when you go beyond node 7, you get node 8. So I want to know the reason behind you choosing node 6 and node 11, the sum to get
plus its own. No, I've corrected myself. I'm now adding another 8. I'm assuming that this is 1, 2, 3, 4. Then I will mirror them. I'm assuming that people will build houses in this empty space in the future. There's a lot of assumptions in this design. Any good consultant, the reasonability of your assumption brings you closer to reality. If some of us design, we say this bill we carry to kilometer. You're not sure? Oh, life load is 3 kilonewton per meter square. Which kind of life load? Are we the same weight? People like me, leave this lift to contain 15 people until you go to Japan and bring your Yokozumas and you tell me 15 people. 15 people, you know, it's assumption, but reasonable assumptions. So when I assume here is 4, now I've assumed that people here will build houses in the future. So I'm now assuming 8 houses. Here I assume 20 houses. There are about 25 houses. I just assume 20 to make it because I want to be lazy. You multiply 20 by any value, just multiply by 2 and add behind it. So now, for this node 7 now, what do I do now? I will now come here. I will now say 8 houses. So I'll say 8 times 0.023. What's the value? .023 times 8.
0.184.
So the real value for node 7 now is 0.184 plus node 6 0.65.
Can you read what you said about node 7? You said node 7 equal to node 7 plus node 6 plus node 11. Is it node 7 or node 8?
Node 7, I'm sure of what I did. Just take it that way, sir. That's what it is. Just leave it that way.
Okay.
That first node is like its own demand plus
its
the
own
demand
value.
of 2 downstream.
Other one.
What he's wondering is node 8 not part of the downstream of
node 8 will be node 9 plus node 7. Don't worry, we are still at node 7. I know what I'm saying.
That's what he's trying to understand. Is node 8 not part of the downstream of node 7? That's what he's trying to
understand. No, it is not.
So now, I'm going to do node 8. But before I do node 8, I need to do node 9. And before I do node 9, I'll first do node 10 and node 12. Do you understand the pattern? So next, I'll do node 10. I'll do node 12. Then node 9 is now equal to, we're ending the class now. Will now be node 10 plus 12. Are we together? Did you understand it?
What about node 9?
If some of them, they don't have houses attached to them, I'll still come to that. Those houses attached to them, you can put it in node 10 or you can put it in node 12. If you look at how the structure is. You have a point. In case sometimes the default demand will be 0. Don't forget that. After that, I will now come and do node 8. And node 8 will now be what? Node what?
Node I want to ask you something based on what you just said last.
Before you ask me, if there's a water pipe passing through your house, you will take the one you will use for your house. The remaining one will go up downstream. That's what it is. So if I'm calculating the water demand at my node, it will be those downstream plus my own I'm going to take in.
Yes, exactly.
But that's not what I
my
want.
Own default.
That's not what I wanted to ask.
Okay.
You said at times there are points the default node is 0.
Because I can locate a node where there are no houses. Assuming my house now, there's nobody living inside, let's say. Or it's just for structural or design purposes. I locate a node where there's for instance, there's no node in node 1. There's no houses attached to node 1 from our drawing. So the node value there will be 0. Did you get it?
So there's no water flow going to that node from the subsequent
No, there's
node.
water flow, but there's no water. That is the point. That is what I want everybody to understand.
There's flow, but there's no usage.
There's no usage. God bless you. That's the word. Maybe you're from water corporation. There's no usage, but there's water there. But it's not for him. It's for those downstream. Gentlemen, what we have done today is you just have to understand it. If you don't capture it, ask your question, because this is the crux of it. You must understand that gradation. That's the problem of Nigerian engineers. We have done this training with more than 500 engineers. This is where the problem is. If you get this right, I've already done the exercises to do, which is what I'm going to do. Please, how many people did our assignment? Because almost half of the class, we were 20 last week, we almost started now. So I'm going to defer our assignments. Please, if you have done it, good and fine, because there's a new assignment now. I want you to print this table and fill it. All this value I'm saying, no this, no this, no this. Fill column. You can send out to fill it, no problem, no penalty. See this column on the demand. Fill it. We have done node 13, we have done node 6, we have done node 7. We have done node 13, we have done node 6, we have done node 7. Fill all these nodes, fill the values here. And then make an attempt to get me the pipe diameters. If you don't get them, they won't come for next class. We will now review and see who got it and who didn't get it. The good thing is that in trying it, you can make mistakes and you can send questions on the chat on the WhatsApp group, and I will find out and answer you. Or somebody else will answer it. We are 30 in number. There's no way you ask a question and someone will not ask. The problem is, will you ask a question? So go and fill this. Then those who didn't come last week, please, for you to be carried along, watch the video and then do the assignment. The assignment is just chapter 8. Is it chapter 8? With the next class, that assignment is as simple as ABCD.
Hello, Engineer Uche. Hello, sir.
Yes.
Sir, I want to ask a question.
Just a clarification. Can I ask?
Yeah, go ahead.
Go ahead.
Okay, in that assignment, you say we should use a slope of 0.3%.
No, 0.5. Just let's continue with 0.5. Any slope use is inconsequential.
Okay, the one you mentioned before.
It's just for you to understand it. 0.5 here.
The one you gave us, you say 0.3. Should we use 0.5?
Use 0.3.
0.3%.
Yes.
Okay, so what will it be on the nomogram now?
That is why it's an assignment. It will be 3.
It will be 3, not 0. Okay, it will be 3 because of the per mil.
It's an assignment. Okay. It's an assignment.
Okay, because of the per mil. I get it.
Sir, I want to ask a little question about the table itself you asked us to fill. On the distances between two nodes, is it gotten from the design of the road, the distance?
Horizontal measurement, yeah, from the design of the road, yes. Horizontal measurement. You just use AutoCAD too.
Okay.
Design of the road.
Okay.
So, gentlemen, this is our assignment. We say that this is the water demand for all this region. We say, what is the pipe size? The main pipes going to this region. Calculate the main pipes. That's what it is. But I gave a warning. I said in Germany, comma means point. So this is 198.8. This one that you see 2 points, something. No, it's 2,948.8. This one is 240.3.
I can't see your screen, sir.
This assignment we gave you is under.
We can't see your screen. We can't see your screen.
We can't see what you are talking about, sir. Okay.
This is my screen.
The important thing is that they are.
Okay, that is last week assignment.
Yes, this is last week assignment for those. So those who don't come last, who didn't come last, we have to assignment. We have 1 week to do it. Please. I know it's not easy, but I'll do it from find time. So you convert this to liter per second. You get the pipe size. You convert this to liter per second. You get the pipe size. This is 920.2. Convert it to liter per second. Get the pipe size. I mean, it's very simple. You've done it today. So just do it. Then you now fill this. Now, this is an expo, but I wish somebody would not take a look at it. This is actually the, okay. I'm going to finish us now. The thing is here, but I don't know how I'm going to put it. Okay, for the assignment, hello. Are you with me?
Yes, sir.
Yes, sir.
Yes, sir.
For the assignment, each house contain 30 persons. You know, we say 10 persons. So those houses are two suspended floors. 30 persons per house, not 10 persons per house, because some of you will go and check this one and copy it. So, but then it is good. I've changed it to 30 persons per house. Case closed. 30 persons per house. Assume a slope. Listen to this now. The slope now is 0. The slope now is, I'll put on the WhatsApp group. The slope now is 0.01. No, the slope now is 0.1%. 0.1%.
0.1%.
Yes, for our new assignments, assume a slope of 0.1%.
We are already assumed for 5 now.
I said I've changed it now, so I don't copy. Assume a slope of 0.1 and 30 persons per house, not 10 persons per house, 30 persons per house. So it's like a duplex or a high rise.
0.1.
I'll put on the WhatsApp group 0.1% and 30 persons per house. Please get me the pipe sizes from 1 to 30. Thank you. Please let us end the class here. We have exceeded our time. I know you have questions, but please let the questions be asked on our WhatsApp group so that